Hello. In this video, I'd like to talk about linear regression and look at the four main pieces of regression, see how they fit together. We said that linear regression seeks to find a relationship between two variables that are related. For example, the number of times a student attends class and that person's grade on the test. We would think that the better the attendance, the better the grade, giving us a positive relationship. Another example, the number of problems a student can correctly solve and the grade on the test. Once again, a positive relationship. We could also say, what about the number of times a student missed class and that person's grade on the test? And that would be a negative relationship. As the absences increase, the grade would go down. Another example, we can talk about something out of forensic science, where they find footprints at a crime scene. And there is a relationship between the length of the foot and the height of the person. Again, the belief is the longer the foot, the taller the person. So when we believe we have a relationship between two sets of data, one is called the predictor, the other the response, we first go out and collect data. So this first step would be to collect our data. Now, when we gather the data, we are collecting paired data. So, number of classes attended, grade on test. Number of problems solved, grade on test. Number of absences, grade on test. Foot length, height. So this data that we are collecting is paired data. And once we collect the data, we will then put that data into a scatter plot. And we want to see if the scatter plot indicates a linear pattern. And that could be one that's increasing or one that's decreasing. So this scatter plot would suggest that there is a positive linear correlation in these two sets of data. The X value, if you will, is the predictor, and the Y value is the response. So once we have collected our data and we've constructed our scatter plot, we then want to come up with a measure for the strength of this linear relationship. And so in step 3, we will calculate the linear correlation coefficient. The symbol for the linear correlation coefficient is R, lowercase r, and R will always be a value between -1 and +1. A value of -1 would be perfect negative linear correlation. A value of 1, perfect positive correlation. A value of 0 would say there is no linear correlation. It could be another type, it could be quadratic, it could be exponential, but an R value of 0 would tell us there's no linear correlation. Now, how strong R is, the closer to 1 or -1, the stronger. If we're satisfied with our value for R, then we will calculate the regression equation. So in step 4, if we are satisfied with R, we'll use R to calculate the regression equation. We remember from algebra that the equation of a straight line in slope-intercept form is y equals mx plus b. So we're ready to calculate our regression equation, and we'll use the form y equals mx plus b. I need two values. I need a value for the slope of the regression line and a value for the y-intercept, b. To find m, I'm going to take the value I found for r, and I'll multiply that times the standard deviation of y and divide that by the standard deviation of x. And that gives me my value for m. I now know m. Now to find b, I take advantage of a marvelous fact, which to this day blows my mind. And that fact is this, that every regression line for a set of data will always pass through the point x bar, comma, y bar. So the point x mean, comma, y mean is on every regression line. So knowing that fact, I can replace y with y bar and x with x bar. Now I know m. I have to find b. So let's use a little algebra and make this happen. So I want b by itself. I'm going to subtract mx bar from both sides. So the equation will look like this. And let me keep the writing here. So negative m times x bar plus y bar equals b. And this gives me the value for b, which is great. So I have my value for m, and I have my value for b. So I rewrite the regression equation in the form y equals mx plus b, using the value I found for m and the value I found for b. Very powerful things. So here are the 4 steps. I've got an idea, I collect my data, put that data into a scatter plot, find r, and calculate my regression equation. Now I'm going to show you how we find r by hand, but our calculators are equipped that when we enter our data into our calculator or into a computer program such as Minitab or StatCrunch, it will give us this output. It's nice for us, though, to know where that output is coming from. How are we getting those values? So if I want to find r by hand, let me show you how I'll do that. But before we leave this equation, once I have this regression equation, I can use it to make predictions. So I've got an equation, y equals mx plus b. So if I have a value for x, I can input the value for x, and the value for y that's produced will be the response. It will be the value I would expect from my regression equation, the predicted value from the predicted value of x. Alrighty, let me show you how we would find r if it were not given to us on a calculator and I needed to do the process it by hand. So I've got my data, X and Y. I've got those data points. And I would want to find the mean of X and the mean of Y and the standard deviation of X and the standard deviation of Y. So I have my data, and I would find the mean of X and the mean of Y, the standard deviation of X and the standard deviation of Y. Then what I'm going to do is create two columns, and I will find the z-scores for each X value and the z-scores for each Y value. So I've got my X values and my Y values. And I find the z-scores for each X and the z-scores for each Y. Then what I do, I'm going to multiply these z-scores. So this column will be a column of the products of the paired z-scores. The products of the paired z-scores. So I multiply the paired z-scores. Here are their products, and I'm going to add that up, and I get the sum of those products, zx times zy. Now that I have that product, I take that product, I divide that by n minus 1, n would be the number of pairs of data. So if, say, I had 20 pairs of data, n minus 1 would be 19. And I'll divide that, and that gives me my value for R. So again, this regression equation, this regression line, has two other names. It's called the line of best fit, and it is also called the least squares line. The reason for this line is going through our data points, and it's the best fit. It's the best line we can draw through our data points. So, for example, let's say here's our points, here's our line. This is the line of best fit. Now, I mentioned that the point x bar, y bar is a point on that line. The other points will be above or below the line. Maybe one or two may actually be on the line. Now, the difference between a point and the line, this vertical distance, you see some of these points are above the line, some of the points are below the line. So these differences or distances, these are called the residuals. Above the line, the residuals are positive, and below the line, the residuals are negative. So to nullify the negative positive effect, we square the residuals, and then we could add them up. So we would come up with a sum of the squared residuals. Well, this regression line is the line of best fit because this regression line is such that it minimizes the sum of the squared residuals. And because it minimizes that sum, it is therefore the best fitting line, or the line of best fit. I hope this helps clear up and clarify in your mind the process of linear regression, what is involved in finding that line, and the meaning behind the term best fit line least squares line and the idea of residuals and minimized sum of squared residuals. Hope this helps.